Welcome back. We're going to compare exponential and linear functions now. And hopefully by the end of this you can see how we find formulas for linear and exponential functions. You are very familiar with linear. We've done this a ton of times, but now we'll be doing exponential. We'll be finding a lot of formulas and solving some graphically, equations graphically. So let's start with some comparisons. Y equals b plus mx is linear. Y equals ab to the x is exponential. For a table of data that gives y as a function of x and in which the change is x is constant, if the differences of the y values is constant, then it could be linear. If the ratios of the y values is constant, do you see the difference here? If the ratios, the table could represent an exponential function. So let's continue on. Let's look at also the similarities and differences. Well, here I have y equals b plus mx. If you'll notice, when you have this, I have my initial value, and I'm adding my slope or subtracting my slope so many times to get my value. And then when it's linear, you're taking your initial value here of a and you're multiplying it as many times as, or raising to the x value. Linear functions repeat sums, whereas exponential functions involve repeated products. In both cases, the x determines the number of repetitions. Now, let's look at some more similarities and differences. Linear functions repeat sums, which I just told you, and in both cases, x determines the number of repetitions. So let's do this. We have linear, okay, and linear has b as my y-intercept, okay, and I have y equals b plus mx, and the slope is your constant value that's repeated. In exponential, a is your y-intercept or your initial value, and b is your repeated ratios. In y equals ab to the x, the value of b gives the growth factor and a gives the starting value, like we've shown before. Let's practice a couple tables here. Here's our first table. And I want to see if it's linear or exponential. Let me make sure I didn't skip a slide. No, I didn't. Okay, so I have a table here. This x value goes for both of these. So x and f of x is a graph, and then x and g of x is a graph. So we have to determine which one's linear and which one's exponential. Well, the first thing is I do my delta x's here, and you'll see my delta x's are going up 5 each time. So that's pretty constant. So I said, okay, my delta x is 5. Now let's look at f of x. So we're going to do some carets here. I see that I'm going from 30 to 45, so I'm going up 15, going up 15, going up 15, and I keep going. So it looks like maybe f of x might be linear because it's increasing 15. My delta y is 15 and it's 5. So my slope is really 15 over 5 or 3 each time. Okay? So if you'll notice, if I do 45 minus 30, I get 15. Then if I do 60 minus 45, I get 15. And so on and so forth. It could keep going. So this looks like it's constant. So that could be a linear function. We're not finding the formula, we're just determining if it's linear. Let's look at g of x. Now when I do the carets between here, do you notice this is going up 200, but then it's not going up 200 each time, it's changing. So if I want to check to see if it's exponential, because exponential is ratios, what you do is you take the second value and divide it by the first. So if I take 1200 and divide it by 1000, I get 1.2. If I take 1440 and divide it by 1200, I get 1.2. And if I keep doing this, I'm going to get 1.2 each time. So this is constant, but it's a constant ratio. So this must be exponential because it's a constant ratio. So let's write this down. Constant ratio. This is just a constant number here because we're subtracting the 2. So let's look at some tables this way. The following tables contain values from an exponential or linear. And I want to find in each table which one's exponential and which one's linear. So let's see if we can find a possible formula. So this one right here, I see my delta x. We'll do our carets. It's going up 1 each time. And if I do my carets here, it looks like it's increasing 10, and so forth. So this one looks linear. So I'm going to say this one looks linear. And the cool thing about this is they gave us the initial value, because at 0, the y is 65, so that's my y-intercept. So I say y equals b plus mx. I know that it starts at 65, and my slope is delta y over delta x, so it's 10 over 1, 10 over 1, so my slope is 10x. You can stack and rack a couple points, and you will still figure out the slope will come out to be 10, because it's 10 over 1 each time. So we found our formula. Now let's look at this one right here. I look at my carets, they're going up by 1. And here it's going up by 200, by 300. See how it's not constant? So as soon as I see it's not constant, I'm going to do the ratio thing. So I'm going to take the higher one divided by this one. So I get 600 over 400. And when I do that, I get a 3 halves, or 1.5. And this one's 900 over 600. And when I do that, it's 1.5. And then 1350 over 900, get the idea? It is 1.5. So I see that my ratio is constant. Sorry. So this must be exponential. And if this is exponential, then what I'm going to do is do the formula here. So the formula is a b to the x. Now the only reason why I know this is my growth factor is because this is a 1 here. This doesn't always happen. It's cool here. This is my initial value. So I have y equals 400, and my growth factor is 1.5 to the x, which means it's actually growing 50% each time, because if I subtract the 1, it's growing 50%. Okay, now if I'm going to find some formulas here, I'm going to look for some formulas here. First of all, there's 2 different ways to do it. There's case 1 and there's case 2. Right? So case 1 is basically when they give you the y-intercept. If they give you the y-intercept, there's only 2 steps. It's very simple and it doesn't take very long. The other one is if it doesn't. So I'm going to stop this tape for right now, and then I'll come back and we'll finish this.